All right, ladies and gentlemen, and welcome to today's class. So, today's class talks about the development of a new atomic model. So, we're starting a new chapter, and it to kind of contrast a little bit from what we did in our last chapter. In our last chapter, we talked about the development of the atom from John Dalton, who proposed the first atomic theory, stating that all matter was composed of atoms. Well, at least John Dalton proposed the first formal atomic theory. We know that prior to John Dalton, the Greeks had kind of philosophized about the composition of matter. But going back to Dalton, he proposed the first atomic theory, and we talked about the law of definite proportions. And all this was done in about the 1800s. And in the 1900s, scientists kind of developed a new atomic theory. And one of the things that they did was they started to study the composition of light. And there were numerous ideas that later on gave way to theory for scientists like Albert Einstein's theory of where he said that E equals mc squared. But all that had a beginning, right? There was a beginning to that part. And what I'm going to do in this video is go over the first couple of pages of section 4.1 of your textbook. I have written down or spaced out the most important parts of this section to kind of summarize what we did today in class. Hopefully this video will be helpful in understanding what you guys have to do. So let's go ahead and start with the first point. So the first point, like I mentioned, it says that before 1900, scientists thought that light behaved solely as a wavelength. Okay, scientists thought that light could only possibly behave as a wave. It didn't, I wrote light here, but I meant to say wave. Okay. Scientists realized that light could only travel as a wave before 1900. They didn't expect light to be, to have any other properties, because the reality is that light isn't something like, the mass of an object where it's tangible in the sense that I can pick up a sample and just weigh it, right? So they just solely thought it behaved as a wave. Then, as time further developed, they talked about visible light. Now, I mentioned this in class, but visible light that we perceive is not just one big white light, but actually visible light is kind of like a rainbow. And we have a spectrum of different colors in that rainbow, right? We all know that we have purple. Well, that's not purple, but give me a second. We all know, wait 1 second. There we go. We know that we have purple in the rainbow, right? And that purple, then we have kind of like blue. And I'll try to do that real quick. We have blue. We have green. We have green. We have yellow. We have orange. That's not orange. Sorry. We have orange. And we have red. Okay, so we have orange and we have red. So what this is light in reality is this. It's just that the light travels so fast, and we're going to talk about that in a minute, that our eyes only perceive like light as just this white beam. But the reality is that light, there's a spectrum, and it has all these colors. And this is visible in the rainbow when after it rains and the sun begins to hit the earth and the water begins to evaporate. It actually, as it goes back into the atmosphere, it slows down enough where the light emitted from the sun actually is the speed of the light that's emitted from from the sun is actually able to slow down, and we can kind of perceive the colors, right? But visible light, how did scientists define visible light? Well, visible light is a kind of electromagnetic radiation, which is a form of energy that exhibits wave-like behavior as it travels through space. So again, it's a type of radiation, of electromagnetic radiation, that exhibits wave-like behavior as it travels through space. Remember that we get our light from the sun, and those the sunlight rays or the UV rays travel through space where it's mostly empty. And because it's mostly empty, we perceive light to be mostly this white beam. But as you can see, together, all forms of electromagnetic radiation form the electromagnetic spectrum, which is this. So visible light is basically an electromagnetic radiation, which is a form of energy that exhibits wave-like behaviors as it travels through space. In other words, that white beam that we perceive. But together, all forms of electromagnetic radiation form the electromagnetic spectrum, which we commonly call the rainbow, which is this right here. And interestingly enough, now that we're talking about the speed at which light travels through space, we have that light in an empty space travels at 3 billion meters per second, or 3 times 10 to the power of 8 meters per second. So let me try to erase this real quick for you guys to explain something. So light, and I'll draw this. We have Earth. You know what? We'll draw the sun, which is not this color. We have the sun that is actually shining on Earth. And again, I'll try to draw Earth as this blue dot. Because of course Earth is mainly surrounded by water, but we have Earth, and we'll have something that looks like an Earth illustration, countries or whatever. So you guys have an idea. This is Earth, and these are the countries, whatever. When the light, actually the sunlight, travels to Earth, it's empty. That means that between the sun and Earth, although the sun is millions and millions of miles away, but between the sun and Earth, there is an empty space. There's no particles here. It's just space. So that means that when they travel the Earth at 3 billion meters per second. But the speed of light can be slowed down. And I was explaining in class today that if you took a pencil and you poured it into like a glass, poured a glass of water, and you took a pencil and the water here, and you took a pencil and you poured it, but you put it in the glass of water, it looks like it's broken. It's like half of it'll look this way, the other half will kind of look like this, right? And it's because, and I was explaining, and I'm gonna, when I was in school, we didn't have we had mechanical pencils, but everybody mainly used these, so that's why I'm drawing it in yellow. But basically, if you had a pencil, let me draw red for the eraser. If you had a pencil and you put it in a glass of water, there's my super pencil. If you have a pencil and you put it in a glass of water and it looks like it's kind of broken, it's because the speed of light is actually being slowed down by the water. And this is very similar to how our eyes work, because there's a humor, a liquid, right, in our eyeballs, which are the receptors, and it kind of slows down slightly the speed of light, and it helps our brain form the image that we see. So again, the speed of light in an empty space, no resistance, no particles, no water, anything at all, travels at 3 billion meters per second. And again, now we're going to define what wavelength and frequency is. So wavelength is the distance between the corresponding points on is the distance between corresponding points on adjacent waves. It may be expressed in meters, centimeters, and nanometers. So if you go back to the drawing of the rainbow, the wavelength is kind of like the distance. Let's say I have a red wave here, and then I have an orange wave here. So basically, the wavelength. Wait, it's not orange. The wavelength is in fact the distance between the orange point and the red point. If we're looking at the spectrum, so the wavelength is the distance between these 2 points. That's what the wavelength is. So like the distance between the orange and the red, that's the wavelength. It's how close they are, and they can be measured in meters, nanometers, and centimeters. Now, if we talk about frequency, it says that frequency is defined as a number of waves that passes through a given point in a specific amount of time. So frequency, if we look at the sunlight, right, and we go back to the glass, the pencil appears to be kind of broken, even though it's really not. And that's because water slows down the frequency, and the frequency is the number of waves that passes through a given point. So it slows down the frequency of the UV rays of light, or it slows down the frequency of light. That means it slows down the amount of light that passes through a given point. So frequency is defined as a number of waves that passes through a given point in a specific time, usually 1 second. And then finally, we have, it says that frequency is expressed in waves per second. So frequency is expressed in a unit called hertz, and it's named after Heinrich Hertz, who was a German scientist who studied wavelengths. And there's a mathematical equation for it, which says C equals the wavelength multiplied by the frequency, where C is the constant of the speed of light. This lambda is basically the wavelength of the electromagnetic waves, and the V is basically the frequency. So basically, the constant speed is wavelength, which we know is the distance multiplied by the time. Okay, and this gave way later on. This formula gave way to Einstein's E equals mc squared, and we'll see that a little bit later on in the chapter. I mean, it wasn't that Einstein got it directly from this, but it did serve as a basis for it. And now we're going to talk about the photoelectric wave. So the photoelectric wave is the emission of electrons from metal when light shines on the metal. So what this is trying to say is that basically, if we have a metal, whatever metal, and we have light, it says again, the photoelectric wave is the emission of electrons from metal when light shines on a specific metal. So let's say we have metal, and you know what? Now that the sun is, I drew the sun, I'm going to keep using the sun as an example. And let's say that metal is exposed to the sun. And obviously the sun, the light of the sun actually, you know what? No, never mind. Let me just, maybe that can be confusing. So basically what the photoelectric effect is saying is that if light shines on a specific metal at a given frequency, that's going to cause the metal to emit electrons. And this is kind of a way that you can, or a way that you could kind of see it, is if you touch a cable after like a TV cable or something after a specific amount of time, you'll see that it's hot, and that's because electrons are being transferred. So the photoelectric effect is that when light shines a metal at a specific frequency, and later, and we're going to leave it up to here, but scientists didn't know why it was at a specific frequency, and that led, of course, to other developments. But basically, what the photoelectric effect is saying is that when light shines on a metal at a specific frequency, it actually helps the metal transfer electrons. And of course, we know that metals are a good conductor of electrons, and that's why we have copper, and we have bronze, and all these other metals that are used as conductors of electricity. And even if you touch a cable of a electronic device, and sometimes it's warm, it's because of the transfer of electrons, and that's the friction that it causes. So basically, the photoelectric effect is saying that when light shines on a specific metal, at a given frequency, it causes electrons, the movement of electrons. And finally, that led to the development of the wavelength theory, where the wave theory of light predicted that the light frequency could supply enough energy to eject an electron. So basically, the wavelength theory is saying, again, and let me read it to you, the photoelectric effect is the photoelectric wave is the emission of electrons from metal when light shines on the metal, and that led to the wave theory, the wave theory of light, which predicted that the light frequency could supply enough energy to eject an electron, meaning that if light shines on an electron at a specific frequency, it can be supply enough energy for electrons to be transferred. So guys, this is a summary of the first couple of pages of this section, the development of the new atomic model. Hopefully this is helpful, and we'll see each other in our next class. So stay safe and bye.